In this last part, we're going to talk about the connections between temperature and light. So before we can do any of that, we need to give ourselves a clear definition of what we mean by temperature. Not just hot objects are hot and cold objects are being cold. Let's formally define this. Take an object, say a box, and inside that box there'll be gas, and that gas is moving around. Some particles are shooting off that direction, others are going down, others are going to the left, to the right, and always bouncing off the walls, okay? So we call this random motion, the random kinetic energy of all these molecules. The box isn't moving, but it'll have a certain temperature. Effectively, it's a measure of the average velocity of every single one of these particles. So if we increase the temperature of the box, to say the box gets hotter is to mean that all the particles are bouncing around even faster. So in a sense, temperature is just a measure of kinetic energy. It's just a measure of how rapidly things are moving. Now, for scientific purposes, we're going to introduce a Kelvin scale. Right? So for reference, in the Kelvin, we'll say water freezes at 273 Kelvin and boils at 373 Kelvin. Right? You'll notice the 100 Kelvin difference between these two. So it implies that Kelvin is related to the Celsius scale, where in Celsius, water freezes at 0 and boils at 100 Celsius. Kelvin is just a shift of 273 Kelvin, or 273 degrees Celsius. And the reason for that shift is this definition of absolute zero. Right? What do we mean? Go back to the particles bouncing around the box, that temperature. As you cool down, as you bring the knob down, these gases will slow down, start moving slower and slower. And so the definition of absolute zero is when all of the random motions, all the wiggles have come to a complete stop. You have literally frozen all motion. Choose that to be our definition of 0 Kelvin. And that is our introduction to what we mean by temperature. Another thing you might recall about temperature is that matter will go through different phases depending on the temperature it's at. And we'll start where we have a solid. Right? We'll follow water molecules throughout all these phases here. You'll have a snowflake or a block of ice. And all that means is that the atoms of H2O, the molecules of H2O, are forming these nice rigid structures. We call it crystalline structures. Now, turn up the temperature, and you'll get to a point where they start to melt. We're breaking these rigid bonds, and you get yourself a fluid. Keep going up. Once you get into around the hundreds of kelvins, those water molecules will no longer be able to hold together as a fluid, so you'll have a nice gas floating around. And now you guys start going up higher and higher, because we'll see things like this in planets and definitely in the stars. Once you get past evaporation, you get to what's called dissociation. What do we mean here is that we are starting to break the molecules apart. The water molecules, even when they were vapors and gas, was still H2O. Once you start to dissociate, the bonds, the atomic bonds between hydrogen and oxygen are breaking. So now we just have atoms of oxygen and hydrogen floating around. Keep going higher, and you'll get to ionization. All right, so once you get into the millions of kelvins, and this is what we call a plasma. Plasma will be this higher state of phase. And what that means is that take a hydrogen atom. Hydrogen has electrons associated with it. Once you've ionized it and turned into a plasma, the electrons can no longer be stably bounded to hydrogen. So the electrons are ripped away. We've created charged matter now. These things are so energetic. They're moving around so rapidly. They are so hot that electrons cannot stably stick to the protons, the nuclei they want to be around. So you have this plasma of charged matter flying around. So there's your different phases of matter that we can see. Bringing our temperature concepts now over to light, let's formally define luminosity as the amount of light leaving a source. Think of it as the number of photons something's radiating. The hotter something is, the more luminous it's going to be, and the more photons are coming out. Correspondingly, as objects get hotter, this is a Bunsen burner at different stages, the amount of propellant that's fueling the fire. And so as this Bunsen burner gets hotter and hotter, it'll get bluer. It's more luminous. There's more energy being radiated away. Going back to the match. The hottest parts of the match are the blue parts, not the glowing parts here, not the red. So once again, luminosity says how much power is being radiated away, how many photons are leaving every second. Seemingly related, but actually distinct from luminosity, will be the brightness, how bright something is. So mathematically, we can say that the brightness of an object goes as its luminosity over 4 pi r squared. Think of it this way. Here's our star. It's luminescing a certain amount of light away. A certain amount of power is constantly radiating away. And as the distance increases over a spherical shell, that same number of photons are being distributed over a bigger and bigger area. So the brightness goes down the further and further away from the object you are. Another way to think of this is to say the brightness, if you know the distance to an object, you sit here and measure its brightness, you can calculate its luminosity. Here, I have a simple demo to show to try and help further sink this idea in. Let's hammer in this difference between brightness and luminosity. Luminosity means just the amount of energy that's being radiated, right? Just the way the rate that energy is being consumed. This is a LED flashlight. It's powered by 2 AAA batteries. And let's aim it at the screen now. And we have a nice bright spot. If I was to turn the flashlight here and shine myself in the eyeball, I'd temporarily blind myself. It would hurt. So there's a lot of energy here, but here's what matters. It's concentrated in a small area. That's the brightness. That energy per area. So how do I reduce the brightness? Well, I increase the distance. Smear it out. Smear it out, smear it out, smear it out. Right? Same energy. It's the same flashlight being powered by those AAA batteries, but now I've spread it out over the entire length of the wall. So it will appear as bright now. Same amount of energy, but the brightness has been diminished because of the distance. Shrink the distance again. Big brightness. Right? No change in the energy, right? It's always the same flashlight. All we're doing when we detect something is measuring the brightness. It's that energy per unit area. Recall from previous videos that by looking at the spectra of light, we can tell what's out there. Now we're saying, hey, if I can measure the brightness and somehow figure out the distance, and we'll discuss methods getting that in later videos. But if I know the brightness that we can easily measure here on Earth, you just look at the night sky and see how bright it is. Get the brightness, the distance, you can calculate the power output, the luminosity of those objects. Building up on this, building more ideas, you can talk about the flux as the total amount of energy radiated per square meter every second, right? How much energy is hitting a given area every second. That's called this flux, and it goes as the Stefan Boltzmann constant. That's what this the sigma is, the Stefan Boltzmann constant. So the flux is sigma temperature to the 4th. Well, from brightness and distance, we can get the flux. The Stefan Boltzmann constant is another constant of the universe that we can measure, meaning that once you have the flux of an object, you can calculate how hot it is. Another relationship, going back to reiterating what we said before, hotter objects. As the object gets hotter and hotter, the flux is going to increase. Flux increasing means the luminosity is increasing. And these are all relationships tying together now. Key point here, measure the brightness, calculate the luminosity. If you have the luminosity, you can get the flux. And with the flux, you can get the temperature of that object. Ever notice a hot object as it starts to glow? This is an example of what we call incandescence. And it turns out not only do all objects glow when they're hot, they'll actually absorb and or emit light. This is all trying to reach a thermal equilibrium. And we'll describe this using a term called blackbody radiation, blackbody spectrums. A blackbody will absorb and emit light at equal rates. What we're looking at here is a plot of wavelength versus spectral radiance. This is effectively another way to measure the flux of an object. How much light is it radiating? And look at these temperature measurements, right? 3,000 Kelvin, 4,000, 5,000 Kelvin. As the objects get hotter and hotter, the curve will peak more and more. This peak wavelength, this is what we're going to call this is the number of photons that are being radiated the most by this black body. But look at the range. Every different wavelength is a different color of light that's being radiated by this hot object. So these black bodies will radiate in it's what's called a continuous spectrum. All these different colors are being radiated across. Great examples are, say, like a light bulb. It's a warm object radiating photons in a spectrum of colors. A property that's going to come up later for us near the end of the semester when we talk about stars. If we have two black bodies, two objects of the same size, the hotter one is going to be emitting more light. It's going to be more luminous. Because it's more luminous, that means it's radiating more energy away. And it's going to emit light at shorter and shorter wavelengths. And that just goes to the hotter it is, the shorter the wavelength of light it's radiating away. Now, all of us are always trying to achieve thermal equilibrium. In examples in the slides here, this will be explicitly applied to planets, but this principle applies to planets, stars, you and me. So here's how it goes. As a black body, we're trying to absorb energy at an equal rate that we're radiating it away. So here's our planet, and it's thermally active, so it'll be radiating thermal photons away. At the same time, we're being bombarded by external photons, mostly from the sun. And if we're at thermal equilibrium, the rate that photons come in, get absorbed, versus the number of photons that take energy away is equal. By analogy, you could think of a bucket that's filling with water. The bucket has a hole in it, and so water is constantly pouring out. Now, if it's at equilibrium, then the water level is going to stay constant. The rate that water pours in is equal to the rate that the water's pouring out. So that's an object at thermal equilibrium. Same amount of light in, same amount of energy in, same amount of energy out. If the planet is too cold, that means that it's radiating photons away at a lesser rate than it's absorbing energy. The water analogy, the rate the water is pouring out is less than the rate the water is pouring in. So the water level is going to rise. This object is going to get hotter to achieve thermal equilibrium. On the other end of the spectrum, you could be too hot. In this case, you are trying to cool off. So you're going to start radiating more photons. You're going to start sending photons out at a greater rate than the amount of photons that you are absorbing. Explicitly, it's the energies, right? You're going to try and radiate more energy away than the amount of energy you absorb. In this example, the water levels is too high. The water coming out of the hole is going to go faster. It's going to gush out quicker to try and bring the level back to a stable equilibrium level. Recall again the plots of the wavelength versus the spectral radiance, effectively the luminance of a black body. And recall that as the object got hotter, the peak wavelength that radiated got smaller and smaller. And that's encapsulated in Wien's law, which just says that the peak wavelength is proportional to 1 over the temperature of the object. Hence, come back to that phrase. Hotter means bluer. Greater temperature, shorter wavelengths. So here's an example where you can rewrite that, and it will give you the proportionality, and you can calculate the temperature of the sun. You look at the sun, and we'll find that the peak wavelength coming from it is around 500 nanometers. This 2,900,000 nanometer kelvins. That is the proportionality from Wien's law. And that translates to the sun having a peak temperature around 58,000 K, or 10,000 degrees Fahrenheit. Combining our knowledge of the planets with the radiation laws, we can actually calculate and later on measure the temperatures on these planets. And notice this downward trend. As we get further and further away from the sun, the temperature of the planets keep going down. And that's because of that inverse squared law. The radiant flux of the sun is being spread out over bigger and bigger spheres of distances away, bigger surface areas. Same number of photons will be distributed over a wider area, so the planets have to cool off in order to reach thermal equilibrium. Now, some comments worth making about this plot here. The black dots refer to what we would predict using these thermal equilibrium calculations. But the orange represents the measured temperatures on these planets. And our measured and our predicted are in pretty good agreement for the gas giants and Neptune and Pluto. Now you get to planets like Mercury and Venus. Mercury has a wide range of possible temperatures, and that's just due to its proximity to the sun. As for Venus, why such a big gap between the temperature on Venus, what we predict versus what we measure? Greenhouse gases. Venus has a lot of greenhouse gases, and that's trapping a lot of energy, which is raising the temperature of Venus. And in fact, same thing is happening on Earth. We actually have a good understanding of greenhouse gases and the effects of global warming because of studying planets like Venus. In conclusion, the energy of a photon is given by Planck's constant times the frequency. The greater the frequency of the wave, the greater their energy. And light comes in a very broad electromagnetic spectrum. As the wavelength gets longer and longer, the frequency gets shorter and shorter to conserve the speed of light. And all atoms can absorb or emit photons that obey their specific properties. These are quantum mechanical properties in nature. And the analogy we want to use is think about bookshelves. Each atom, each molecule has a unique shelf, unique energy levels, and photons must match those energy levels to either be emitted or absorbed or emitted by that atom. Finally, the last two big ones for us will be the luminosity and brightness, where luminosity is the radiant power of an object. Another way to describe it is the photons it's giving away every second, whereas brightness is that luminosity spread out over an area. So with that, we'll call it into this section. See you next time.